In section 8.3, we're going to work with trigonometric integrals. Namely, we're going to integrate powers and products and quotients of the 6 main trigonometric functions and combinations thereof. So before we go any further, let's think about some ways to make things that we already know easier. Now, there are 6 main basic trig integrals. We learned these back in Calc 1. So you have your integral of sine, your integral of cosine. The tangent and cotangent ones, those are a little bit rarer, but the secant squared and secant tangent, those ones work out nicely to tangent and secant, and cosecant squared and cosecant cotangent, those ones work out nicely. The ones with natural logarithms don't work out as nicely. You probably need integration by parts to make those work. All right, so if I let u be ax, if you see ax inside every one of these, or honestly, it could be ax plus b. It wouldn't make any effect on it, even if there was a constant added on in there. Then the derivative would be a dx, right? A times dx, which means 1 over a du would be equal to dx. Now, where am I heading with that? Oh, and we assume a and b are constants, of course, as we do on the formula sheets and the integral sheets. Okay, so where am I heading with that? Well, I can use that fact to come up with new formulas for these, because the integral of cosine is sine, and if it has the ax, it'll have that ax in there plus c. But if I just took the derivative of sine of ax, I would have a, right? And I don't have an a in front, so I'd have to multiply by 1 over a, right? That's where that's coming from. And again, it could be ax plus b in there, and it would still need to be 1 over a out in front. Similarly, the integral of sine would be negative 1 over a cosine of ax. We've actually already used these in some examples in the previous sections, because the u substitution on these is so simple that we basically skip over it and just kind of wave our hands at it. And so now I'm giving you carte blanche to do so. So for these very simple integrals, you can kind of skip over showing all the u sub and just write them. Integral of secant squared is tangent, so it'd be 1 over a tangent of ax. Integral of secant tangent is secant, so, oh, but it's positive, sorry. 1 over a secant of ax. And then this would be negative 1 over a cotangent of ax, and negative 1 over a cosecant of ax. And if you're looking for the formulas on the formula sheet, you're looking for formulas, let me see here, 8 and 9 for this row. Secant squared is 14 and secant is 16, so 14 and 16. And cosecant squared is 15 and cosecant cotangent is 17, so 15 and 17 on your quick reference sheet. Okay, so one of the things we can do is we can look for pairings. So we like to pair sine with cosine. That's a nice pairing. Sine with cosine happens a lot, so like this. Then we can do secant and tangent. That happens a lot. And then cosecant and cotangent. So those tend to be the pairings that we want and we will find, right? If any other pairings are present, you basically use identities to change them, to turn them into these 3 pairings, because those are the 3 pairings we like if we can make it happen. And before we go any further, what are some identities we could use? Well, there's everybody's favorite, the Pythagorean identity. Sine squared plus cosine squared is equal to 1, right? Which is the basic one. It's using sine and cosine. But of course, if we divide everything by cosine in this one, which we could, so if I took sine squared x plus cosine squared x equals 1, and I divided everything by cosine squared, that would give me sine squared over cosine squared plus 1 equals 1 over cosine squared, which would be tangent squared plus 1 equals secant squared. So there's identity number 2, right? That's the secant tangent pair. And then similarly, I could do the same with cosecant, cotangent. So if I took sine squared x plus cosine squared x equals 1, and I divide by sine squared, it would work very similarly. It'll be sine squared, oh, it'll be sine squared over sine squared, which is just 1. Oh my goodness. Cosine squared over sine squared. I'm losing my brain. All right, cosine squared over sine squared equals 1 over sine squared, which is 1 plus cotangent squared equals cosecant squared. So there are the 3 Pythagorean identities. If you know the first one, you know the other 2, because it's not that hard to develop them as long as you remember what you're dividing by. Then there are the lovely half-angle identities, right? The sine squared of theta is equal to 1 minus the cosine of 2 theta over 2. And I know what you're thinking. How is that a half-angle identity? Well, it's because this angle in here is 2 theta. So half of 2 theta is theta, which is exactly the angle that we're talking about here, right? So the angle theta is half of 2 theta. So these are the half-angle identities. All right, so let's try to tackle an integral using the tricks we know and, well, the tricks we know. So when I look at this problem, I think to myself, I think we could use substitution with this. So substitution shouldn't be bad. If u was sine of x, because that's nested inside another function, then the derivative of that is cosine of x. So then what I really have is the integral of u to the 4th du. Okay, well, the integral of u to the 4th is 1/5 u to the 5th plus c, which would be 1/5 sine to the 5th, because u was the sine of x, plus c. That wasn't so bad, right? So that was pretty easy to do with substitution. But that was because there was a cosine there that made the u substitution work, right? So I had the u, which was sine, and it only worked because of that presence of cosine, right? Cosine made the du part and made it all beautiful. But what if we have other powers? Then what will we do? Well, we'll see that in the next video, because that's where we'll start.